Hi friends, it's Darcy. We are here to talk fluids today. We are going to learn about friction and head loss. This is in a PowerPoint / Notability format so that we can look at some figures and tables that you'll need, write some equations, that sort of thing. So that's why this is looking a little different than what you're normally used to. But let's jump right in. We are going to start where we start with a lot of things in fluids, which is with the energy principle. So the energy principle is P1 over gamma plus V1 squared over 2G plus Z1 plus HP minus HL minus HT. Again, if you want these to be positive, you can move head loss and turbine head over to the other side. Inputs, outputs, if you need to think of it that way, that's also fine. Whatever works, positive or negative. Just make sure it's on the right side. And then we have P2 over gamma plus V2 squared over 2G plus Z2. So what we're going to look at today is this middle head loss. So we've talked about head. Maybe you haven't quite grasped what head is yet. It's a hard thing to visualize, but we're going to look at head loss today. So when we talked about head is just a way to measure pressure or energy in a system. There's different types of head, the main being static pressure, dynamic pressure causing different heads. In this case, we are going to see a loss of head, so a loss of pressure or a loss of energy due to friction. That's what it really comes down to, is frictional losses in a system. Remember, if we look at a pipe where we are measuring just simply the static pressure of a system, in this case, the fluid line here would be here. As we go down the pipe, even if there's nothing else in the way, we are going to lose the pressure. That's what we're looking at, is this head loss in between height 1 and height 2. This can also be related to the pressure fluid height principle. We're not going to talk about that today, but think about how those two things connect and what this difference in H means, that loss in height. We're going to talk about how to actually find this head loss, this loss in pressure, loss in energy because of friction. So there's two different types of losses that we're going to look at. The first is minor losses. The other is we call friction losses. This can also be called like major friction losses. But let's start with minor losses. So minor losses, we are going to have the equation HL is equal to K V squared over 2G. Part of this equation should look very familiar. Specifically, this V squared over 2G should look very familiar because we just saw it in our energy principle, which in this case, this is our velocity, just a measure of our velocity head. And if you remember what velocity head is equal to dynamic pressure over rho g. And our dynamic pressure here is equal to our kinetic energy per volume. So basically, our velocity head is a measure of our dynamic pressure, which our dynamic pressure is a measure of our kinetic energy per volume. Really, we're just measuring that pressure or head that is due to the movement of the fluid. So if we look at this equation for minor losses, this is just simply a friction coefficient. And whatever that number is, it can be below 1 or it can be above 1. So we are losing a certain amount of heads, velocity heads, based on that friction. So like if I have 1 times this V squared over 2G, which is a velocity head, this friction coefficient is causing us to lose 1 velocity head because of whatever friction is in the system. Maybe it's something that's less, it's only 0.2. So we're only losing 0.2 or 20% of a velocity head. Maybe it's something bigger, maybe it's 100. This K is equal to 100. We're losing 100 velocity heads. So 100 times that velocity head equation is our head loss. Let's talk about some of those things of what that, I guess, what contributes to that friction coefficient. So you can look up these tables, just Google them, about minor losses due to valves or T's or elbows, whatever. But basically we're looking at a system where maybe we have just a length of straight pipe here, but we put some sort of valve into this system. This is a very accurate picture of what a valve would look like, obviously, but we have a valve in this system. So in this valve, it could be a lot of different things. It could be a globe valve, angle valve, gate valve, swing check valve, ball valve, diaphragm valve. It could be a water meter, whatever it is. We have some sort of valve in there. And this friction coefficient, we have a different Greek letter here. This is just our K. Sometimes you'll see it as a C as well. It's just our coefficient of friction. And if we go to, say, a gate valve and it is fully open, our frictional factor is only 0.15. Not huge. We're only losing 15% of a velocity head because of that valve. But if we close that gate valve 3/4 of the way, our frictional factor is now 17. So if we go back to this equation and plug in 17 for this K value, we're getting 17 times velocity heads, and that's what our head loss is, which is a lot. And you can see there's other ones that are even more, like a ball valve. If we close it 2/3 of the way, it's a frictional factor of 200. A water meter itself is a 7. So we have these different elements that we can add into a pipe that are going to cause different amount of losses. We could also have elbows here. We could have some sort of like T's where we start to split the flow. And all of these are going to cause different amounts of losses depending on what we're doing with the fluid. There's obviously going to be some losses as this fluid moves around an elbow. There's going to be some losses as this fluid breaks into 3 separate streams. And the nice thing is K can be summed. So say I have, let's say this is a gate valve fully open. So I'm going to do 0.15. Let's say this is, so that's where I'll point this out here, 0.15. And then let's say we have a, I don't know, an elbow threaded long radius, 90 degrees. So we have plus 0.7. And then we also have a T, it is dividing line flow. So we're going to add 0.9 to this. So we can add those up. Oh boy, in my head, 0.22, oh wait, 0.85 plus 0.9. Man, I am the worst at brain math. So 0.15 plus 0.7 plus 0.9, 17, yeah, 1.75. I'll get it eventually. So our frictional factor for this entire system here is 1.75. So then we can just take that whole K value, plug it into this equation here, and get the head loss for that entire system. So that's minor losses. You may see something also talked about that's an equivalent length table. For this class, we're not going to use those, but you have to be careful because it's going to tell you lots of these same things, like how much a T or an elbow or whatever is going to add, but they're going to do it in an equivalent length table. So you have to make sure to distinguish, do I have a coefficient of friction or do I have an equivalent length? I'll talk to you about where that equivalent length can come in our major friction losses, but just be careful when you're looking up tables, you have to make sure it's a coefficient of friction if you are using this minor loss equation. Okay, so jumping to major friction losses, we have HL is equal to FLV squared over, I'm going to write this D times 2G. And I write it that way because, again, I want you to see that we are still relating to velocity heads. And I guess I should write that. Velocity head is the yellow part, and that's the same as here. And what we have in this equation now, this is an F similar to K, but it's called, in our case, we're going to have the Darcy friction factor, and we're not naming it that just because my name is Darcy. This Darcy is spelled wrong, and it was also a dude's last name. So Darcy friction factor is what we're going to use in this class. The L is a characteristic length. And that's actually where that equivalent length can come in, because our characteristic length in just simply a pipe will be the length of the pipe. So maybe we have a 10-foot pipe. But if we put an elbow into that, we could look up the table for equivalent length, and maybe it tells us that that elbow adds 1 foot of equivalent length to our pipe. So we have a 10-foot of straight pipe, but then once we add the elbow, that adds 1 equivalent length of pipe. Again, we're not going to use that in this class. I want you to calculate minor losses and major losses to see the difference. But just so you're aware, if you Google some tables, you might come across an equivalent length table. Okay, characteristic length, we have velocity, gravity, and the diameter of our pipe. So we know how to get all of these things and what to do with them, except for this F. And the reason it's called the Darcy friction factor is because this equation is called the Darcy-Weibach equation. Again, 2 guys' last names, that's where that comes from. And basically it's just relating, as you can see from here, it's relating our head loss or pressure loss that's due to friction along some given length of pipe. It's relating it to the average velocity of the fluid flow, which again, it's the velocity head. It's related to dynamic pressure. It's related to kinetic energy. So think about how all of those things are related and what this Darcy-Weibach equation is telling us. So the question is, how do we find the F? Luckily, Moody wanted to give us an easy way to do that. So we have something called a Moody diagram. So we have to calculate 2 things for our Moody diagram. The first is over here on our right axis, which is called the relative pipe roughness. So relative pipe roughness is epsilon over D. So your epsilon is going to come from this table right here. You could also find, if your material of pipe isn't here, you would be able to find this as well. But these are some common ones. So let's say that we have cast iron pipe here. Our epsilon is going to be equal to 0.15, which make sure you pay attention to these units. This is in millimeters. So then say we have a diameter of a pipe that's 10 millimeters. That is going to then give us a relative roughness. Let's put RR, there's not really a variable for that, but relative roughness is equal to 0.015. So what that's going to tell us on the Moody diagram is we're going to come over here to 0.015, and we are going to follow, in this case, it's a blue line, but if you get a black and white graph, it'll be black probably. And we are going to follow this line. We're going to follow the curve right here. And the reason we follow that curve is because that is going to give us our friction factor. And it's telling us what region of flow our flow is in, which relates to this, whether we have laminar or turbulent flow. And that is calculated by our other variable down here, or that's not, well, yeah, it's calculated. It's told to us by this calculation for Reynolds number. So our Reynolds number is equal to, we usually do RE, is equal to rho V D over mu. And you should know these are density, velocity, and diameter. You may not have seen this before, which is dynamic viscosity. And all viscosity is, maybe you've heard the term, but not really known what it meant. We think of like corn syrup being a viscous fluid, whereas something like oil or water is a less viscous fluid. What that means is the dynamic or the absolute viscosity of a fluid is the internal resistance to movement of one layer of that fluid over another. So think in corn syrup, there's going to be a lot more resistance than in something such as oil or alcohol or something like that, that isn't as viscous. So That's what dynamic viscosity is. And that makes sense in the terms of what we're going to look at if our dynamic viscosity, and I want you to think about this, if our dynamic viscosity goes up, if we hold the density, velocity, and diameter constant, what is that going to do to our Reynolds number? Okay, think about those relationships. If you have questions, let's talk about it in class. But there is one other equation I want you to be aware of how they can write Reynolds as well. Reynolds can also be equal to just simply VD over this funky V. And this funky V is our kinematic viscosity, which you can see from above just simply comes from rho over mu. Our kinematic viscosity is just equal to mu over rho. So if we look at the inverse of that and how that works out, those are the two equations you're going to see for Reynolds. And what Reynolds tells us about these flow regimes over on the right side is if Reynolds is less than 2100, we are in the laminar region. If it is greater than 4000, we are in the turbulent region. Laminar flow is just simply everything is running parallel very well down a pipe. You see that there is some curvature, parabolic shape to this because of the resistance that is at the wall versus the resistance that is in the middle of this. Again, viscosity is going to play in that. And then that's why we also do relative roughness, because that's going to play into this as well. And turbulent, we have all sorts of eddies and swirling and curved paths and all of these things going on that it's not a straight flow. We're going to be in the turbulent region a lot, but this gives you a visual of what that looks like. I've also attached a video that you can learn more about Reynolds number and what laminar and turbulent flow means. We're not going to discuss it more here, but you are welcome to watch that video and we can talk about it more in class. Okay. So once we calculate our Reynolds number, we can come back to the Moody diagram. I'm going to say that maybe we have a Reynolds number of 3 times 10 to the 5th. So what I'm going to do is come down to this bottom axis. Here is 10 to the 5th. So that's 1 times 10 to the 5th. Then we have 2 times 10 to the 5th. 3 times 10 to the 5th, which is what I said we were at. So I'm going to draw this line straight up. But you can also keep going. This is 4 times 10 to the 5th, 5 times 10 to the 5th, 6 times 10 to the 5th, 7 times 10 to the 5th, 8 times 10 to the 5th, 9 times 10 to the 5th, and then we're at 10 to the 6th because 10 times 10 to the 5th, simply 10 to the 6th. So remember that's on a log scale. That's how you're going to use that. But with this line, if we're at 3 times 10 to the 5th and we draw this line up, and then we see where it intersects with our highlighted line here, and then we simply do a dotted line across here, we are going to be about, I don't know, we could say 0.045 because I kind of went crooked there a little, maybe 0.4. So 0.044, we could say is our friction factor. So that's what our F is equal to. So we can then take that friction factor, that F, and come up and plug it into our Darcy-Weisbach equation and get our head loss. As I talked about that minor losses can be summed here, you can also sum minor losses and major friction losses to get your total HL for the energy equation. Again, if you're using equivalent length, you would only have to do this side and then you wouldn't have to sum, but we're not going to use that in this class, but it is a potential opportunity. It's something that you may see. You may see it in the FE as well, where they talk about characteristic length, because you're also going to have different characteristic lengths based on your pipe, but we're not going to go into too depth into that today. So there you go. There is friction and head losses. We have minor losses, major friction losses. What it really comes back to is that we're losing velocity heads because of friction. So we have some sort of movement of fluid in a pipe, open channel, whatever. In this case, it's going to be a pipe, and that's causing some sort of pressure, some sort of head. And because of friction and the way that's moving through the pipe, we're going to lose some of that head because of the velocity. think about that, grasp that, bring your questions to class and let's discuss this more. But now you know how to use these equations, especially being able to use the Moody diagram to find F is very important. So hopefully that made sense.